Hi guys, Dr. Mandis here, coming at you today talking about solubility. We've been doing a lot with reactions and oxidation reduction and all sorts of jazz. Today it's a little- maybe a little bit more straightforward. We're going to talk about solubility of ionic compounds, which will lead us into some reactions. Oxidation reduction reactions deal a lot with single replacement reactions. Solubility deals a lot more with just ionic compounds reacting, which turns double replacement reactions into composition or synthesis reactions. Okay, but you have to know your solubility rules. I have mine written out right here. I have two versions, one for soluble ionic compounds, one for insoluble ionic compounds. Okay, they're really typically written for the cation. All right, they come in all sorts of shapes and sizes. Find one you like. Okay, but the thing that I have here that you should know is soluble compounds are dissociate. They're always written as anions. We're going to beat the heck out of them next few a little bit. And your insoluble compounds are exceptions to the rule of solubility, or insoluble compounds are the rule, and the exception will be that they're soluble. Okay? They're usually written, you got to look at for an anion, like in here, you got a carbonate anion listed as insoluble. Well, that anion always has some counter ion that comes with it. Copper carbonate, lithium carbonate, sodium carbonate. Well, those counter ions can create exceptions. And usually you just write the exceptions. Like lithium is an exception. Lithium carbonate would be soluble. But if it was like copper carbonate, copper is not an exception, so it would definitely stick with the rule and it would be insoluble. So we have our soluble compound rules, and for some of those we don't have any exceptions. Okay, and that bears talking about. These are mostly written for anions, but there's only one that's written for cations, and that's the whole idea that group 1 metal ions and ammonium, group 1 on the periodic table, those dudes are always soluble. Doesn't matter what anion they hook up with, they're soluble, no exceptions. Okay, when you read this thing, like I'm saying, hey, chloride right here, okay, chloride is going to be soluble typically no matter what cation he's with, unless he's with one of those three. Okay. Fluoride, on the other hand, going to be soluble like the other guys, unless he's with one of those five. So those are the exceptions. Okay. Soluble, dissociate, insoluble, they're written together. Okay. So soluble ionic compounds dissociate, we would write them as separate ions because that's how they actually are in solution. Okay. Insoluble compounds we would write together because that's how they are. They don't separate in solution. Okay, it's really important that you write what you actually have in solution. Do you actually have ions, or do you actually have a chemical formula? And if you put some salt, go down into your kitchen, put some salt into water, and you say, hey, I got sodium chloride in water. No, you don't. What you have is sodium cation in water and chloride anion. They are separate. And if you've ever dated somebody, broke up with them, and been in the same room with them later, you may realize that you're in the same room, but you're definitely not together. Don't mean to bring up bad thoughts, but definitely not together, near each other, granted. Together, not so much, okay? So there is a difference between whether it's dissociated into ions or together as chemical formulas, all right? You really need to use the solubility rules. A lot of first-year chemistry high school teachers, you let them have it. AP, first-year college students, you tend to have to memorize solubility rules, okay? And there are patterns to them, so you can't pick that up with use, all right? So let's practice this real fast. Alrighty, I'm going to go through it. I'm hoping that you'll pause it and go back. Here we're going to look at potassium, sodium, lithium. These are all group 1 metal ions. Because they're group 1, this is the only time that happens. Group 1 metal ions are always soluble. And so they're always going to dissociate into ions, potassium and chloride, sodium and phosphate. I know I'm scribbling. Okay, lithium and carbonate. Okay. You could have done it by the rules as well. Chlorides are always soluble, phosphates are always soluble, carbonates are always soluble, with some exceptions to some of those gigs. But you'd come back with that they're being soluble. Okay? As far as these two guys go, nitrate, okay, rule for nitrate, let's go back up to that real fast. The rule for nitrate, always soluble, no exceptions. So when we go back here to this groovy little table, we're going to say, hey, he's soluble. And so you're going to write iron 3 and nitrate. If you look at the sulfate down here, calcium sulfate, Well, let's find sulfate on our table. He's up here, okay? Sulfate is listed as a soluble compound, okay? But we're with calcium and he's an exception. Exceptions to the rule. Exceptions to being soluble would being insoluble. So calcium sulfate we would list as being insoluble. And that would not dissociate, and so you would just write it together. Alrighty? So, ionic solutions, reiterated what I said there. Soluble, dissociate, insoluble together. If you look at these two, just to beat it up, we got magnesium nitrate. We talked about all nitrates being soluble all the time. Okay, silver chloride, we didn't really investigate the chloride rule, so let's go up to that really fast. Chlorides, I know I'm scribbling all over this place. This is another exception. Okay, for chloride, if we get rid of some of this, okay, chlorides are soluble, one exception, silver. It's just like with the sulfate and calcium. So chloride's going to be an silver chloride would be an exception to being soluble, which makes them insoluble. So let's see what we got going on there. We say magnesium nitrate, soluble, groovy. So you would be separated into ions. Silver chloride, insoluble. So you would always write that together. Okay? Ionic reactions are just your regular double replacement reactions where you'd have AB plus CD. A goes with D, C goes with B. And you write the formulas. But now you're going to apply solubility. What we were talking about with the sodium chloride. If you apply the solubility rules, then you can't necessarily write a chemical formula together if they're really dissociated. Okay, so you need to be aware of that. Okay, if they're separated, instead of writing this, it'll look like dissociated compounds. Okay, what's going to happen is the opposite ions would attract and make a compound that's going to be soluble or insoluble. So then we have to go and evaluate that via the solubility rules. Okay. And then we're going to have spectator ions, this new groovy little definition. We're going to have ions that are the same on both sides. We have to get rid of them. Okay. And then we're going to write things like net ionic equations. So we've got some examples to walk our way through here of basically converting double replacement reactions into synthesis/composition reactions. Okay. So if we do the reaction of sodium carbonate with barium chloride, we get all of that. Wow, that's a lot. Okay. Well, sodium carbonate is sodium carbonate. Barium chloride is barium chloride. Go over formula writing in another video. Okay. If you have a solution of sodium carbonate with a solution of barium chloride, I just sort of abbreviated that, then you don't really have sodium carbonate. You'd have barium chloride, or barium chloride. You'd have ions. So let's pretend we have the ions. Okay. Because the question is, how do you make these things? Let's pretend we have the ions, and what we're going to do is sodium goes with chloride, barium goes with carbonate. Some students can do it up here, some students can't, because if you notice, subscripts are going to appear and disappear. So, especially if you're a first year student, go to here, write the ions, switch the partners up, who's going to go with whom, write your chemical formulas. All right, now we have to say, well, what's the solubility issue going on here? Am I going to keep them as ions, or am I going to keep them as chemical formulas? What's going on? So here's the gig. If you look at it, and I'm jumping ahead, so I might have to come back and talk about this again. This is kind of like an insoluble line. Everybody's written as chemical formulas. This is like our soluble line. Everybody's written as those ions. So if you find somebody that's soluble, then you're going to put it in its ion form. Insoluble, put in its chemical formula type form. So let's look at those solubilities, okay? If you look at it, we got sodium carbonate, barium chloride, sodium chloride, barium carbonate. We need to say soluble or insoluble. If you go back and look at those solubility rules, okay? Sodium carbonate is going to be soluble, okay? Barium chloride, soluble. Sodium chloride, soluble. Okay, so what we're going to have is, whoops, wrong thing. Soluble, so write them as ions. Soluble, write as ions. All chlorides are soluble except for silver, mercury, lead, so write it as ions. Alrighty. Barium carbonate, insoluble. We didn't talk about carbonates, so let me jump up to slide 1 if I dare. Alright, carbonates aren't there. Carbonates are in slide 2. because they're mostly insoluble with some exceptions. There's our sodium as an exception to that rule. The exception to the rule would become soluble and write it as ions. It takes practice to work in through those rules. So the sodium carbonate, definitely soluble. Barium carbonate, definitely insoluble. Alrighty. We then need to write ionic equations and net ionic equations. For the ionic equations, basically, see what I highlighted? Let's bag the things that aren't true. It's really existing like this. Over here, not existing like that, existing like this as ions. Barium carbonate doesn't dissociate, exists like that. That creates an ionic equation. Awesome. Okay. So that's what we did. We took the things that we highlighted, barium carbonate, and the bottom there, made them an ionic equation. We wrote them in the proper form. If you then look, it looks as if sodium is not undergoing a chemical change. It looks as if chloride is not undergoing a chemical change. So if that's the case, let's get rid of them. If they're not undergoing a chemical change, they're not part of the chemical equation. We just get rid of them. Okay? That's a lot of writing. Okay? First year students, you're going to want to do that up front so you don't mess up, and screw up subscripts, because people that just skip it give me things like Na2Cl2, and it would be just wrong. Okay? But AP type students, your first year college students that get this, all right, what you're really going to look at is say, hey, magnesium with nitrate in this example, silver with chloride. I know this is aqueous, so it's dissolved and it's going to be soluble and be ions. I know this is a solution. So another way of disguising the idea is saying, hey, it's in ion form. So the question is, which one, silver with chloride or option B, magnesium with nitrate, which one gets me to a soluble compound? That would be the product. Okay. Well, if you look at magnesium nitrate is soluble, silver chloride's insoluble. Okay. Well, soluble guys are going to dissociate and we got rid of them. Okay. If you looked at our net ionic equation earlier, the net was just about forming that insoluble compound. Well, our insoluble compound is silver chloride, so we could form silver chloride from the ions of silver and chloride. It's a bit easier to do, man, okay? And that's what you're going to do, alrighty? For my AP students and my college students in general chem, I just want that, all right? And what you got to realize is the whole enchilada, magnesium chloride soluble, magnesium nitrate soluble, silver nitrate soluble, okay? Well, we have spectator ions. Magnesium isn't doing jack. Get rid of them, okay? Nitrate, staying as nitrate, not undergoing chemical change. Get rid of him. Those are your spectator ions. They're watching the action. They're not part of it. Okay, they're not undergoing any chemical change. Alrighty? We can talk about conduction really fast in this. Strong electrolytes, we conduct like non-electrolytes. If you have a lot of ions in solution, then you're going to conduct electricity. Okay? Lots of ions strong, less weak, none. Alrighty? I can talk more about that in a later video, but just in case you're looking for some definitions here, there you go. So pay attention. Learn and love your solubility rules. They're not as ugly and gruesome as they seem. Alrighty, this is Dr. Mandis. You guys take care.